박 박사님 안녕하세요.
네, 교수님 안녕하세요.
네, 제가 이 컴퓨터가 리부트하는 바람에 좀 늦었습니다. 아, 시작하겠습니다. Welcome to Data Science Seminar. Today we have a very unusual topic, the revolutionizing semiconductor innovation. Dr. Jiu Park graduated from KAIST, and then she did PhD at UT Austin, and then she worked on the project called Alpha Chip. It's like Alpha Fold, AlphaGo. To innovate this AI chip, innovate the chip design with the AI. So now she's working for Cadence, and she's a software engineering director. I really I look forward to learning a lot from her talk. Thank you. Uh, Dr. Park, it's yours.
Thank you. Thank you, Professor Cha. And yeah, thank you for inviting me for this seminar. It's my honor to have an opportunity to present in front of you. And I heard that Korea had a long holiday recently, right? Was it until yesterday?
Yes, right.
Oh, okay, okay. So
We are
I
starting to work again.
I see. So I'd like to say thank you to all of you, the students, attending this class and talk, especially in the first class in the morning, 9 a.m., right after the long holiday weekend. So today I will cover the AI, how AI or ML has been used in the chip design industry. So my today's title is Revolutionizing Semiconductor Innovation, the Power of AI, ML in Chip Design, Verification, and Manufacturing. So as Professor Cha introduced, my name is Jiwoo Park, and I'm a software engineering director in Cadence Design Systems. So today we will cover after some introduction, we will cover what are the unique characteristics in chip design in terms of adopting the AI or ML. And we will go over the ML or AI in electronic design automation. Yeah, don't worry, even though you don't know this terminology yet, I will introduce that in a while. And I will cover the ML or AI in verification and manufacturability, and we'll conclude the talk. By the way, this talk is purely based on the public information. So even though I have worked in Google, I had an experience working in Google for Alpha Chip, and also I'm working for Cadence Design Systems. This talk will be based on the public information only, so you can easily search the same contents from Google. Nothing will be coming from the inside information. Just wanted to clarify that. And then a little bit about me, even though Professor Cha already mentioned that, maybe I think it's a good idea to introduce myself to you. So my name is Jiwoo, and then I was born in Korea. I graduated from KAIST. I got my bachelor's degree from EECS. At the time, the school was combined EECS. Right now, I heard that KAIST has separate schools, EE and CS, but at the time it was combined school. And then,
It even has a separate AI graduate school. AI
yeah, I
school.
heard that. It's diverging so rapidly, so I cannot catch up
Uh-huh.
the exact name of my own department now. But anyway, so at the time I graduated the School of ECS, and then I took more courses toward the EE, electrical engineering. So my specific major was EE, and then I got my master's degree from the same department, KAIST MS degree. And at the time, I was working on the very early version of 3D IC. So like something similar to HBM. So they are stacking multiple chips together, and what will be the electronic noise there, and that kind of things. So I studied a little bit about that. And after that, in 2009, I moved to US, pursuing my PhD degree. So I went to Texas, Austin in Texas. So I got my PhD degree from the University of Texas at Austin. And fortunately, I met my PhD advisor, David Penn, and he's one of the renowned professor in the EDA industry. And I think the moment that I joined my PhD research lab shaped my journey afterwards. So that shaped my career. So I studied about this EDA topic. Yeah, again, I will talk about what EDA is, so don't worry about it. I learned what that is from my graduate school during my PhD study. And after that, I had an opportunity to work as an intern in Cadence Design Systems, the current company, as a software engineering intern. And since then, I worked in Cadence Design Systems. And during COVID, it was coincidentally aligned with the COVID time, but 2019 to 2021, I had a chance to work in the Google Cloud. And as Professor Cha mentioned, I had an opportunity to contribute in the Alpha Chip project at that time. And after that, Cadence, gave me the offer, so I came back to Cadence. So I'm working as a yeah. Sorry. Yeah, if you have any question, please let me know. So as a software engineering director, usually my day is filled with a bunch of meetings to lead software engineering teams, and then leading multiple projects in the EDA field. And then I live in San Francisco Bay Area, Silicon Valley, and I have two daughters. So one is 7th grader, like Jung-yi, 7th grader, and 2 years old toddler. So very busy, but having fun both at work and home. So that's a little bit about me. Okay, now moving on to before going there, actually, I have a question to all of you. So probably you are using a cell phone, right? Whatever cell phone that is, and a laptop in front of you. And there would be a processor, like a CPU or sometimes AP. The CPU chip, let's assume that you have a CPU laptop, and I'm sure that will have a CPU. And can you guess how many transistors will it have? Just a rough estimation, like tens of thousands or tens of millions. Anybody? Come on, Seoul National University. Yeah. Anybody? If this is an in-person meeting, I would give some goods, right? Some small dolls or something. But since this is online, yeah.
There's one reply on the chat window.
Oh, okay. I cannot read the chat. Sorry about it.
Yeah.
Few billions. Yeah, that's close enough. That's close enough. Okay, so let's move on to the next page. So I just grabbed it from the Wikipedia. As I mentioned, all the informations are public information. So I got this chart from the Wikipedia. Transistor count, you can search it. So this page is showing actually, I think it's intended to show the Moore's law. Maybe some of you already heard the Moore's law, but it's basically the trend of the number of transistors inside of the microchips. And you can see that the chart starts from 1970, and then it's still a little bit old chart, so it ends in 2020. And you can see that the transistor counts increases exponentially, right? This is exponential scale. So you can see that it was just a few thousand in 1970, but now it's like tens of billions. It depends on the application nowadays. It was well aligned with this trend until recently. But nowadays, because the transistor sizes are so small, and then there could be a lot of side effect to pack all of those in a small area, such as thermal issue or electrical noise issue and so on. So depending on the application, now there are more variations. So some chips for the application, certain application may have a smaller density, smaller number of transistors, and high performing chips may have more and so on. But the key point here is the number of transistors are tens of billions scale. And that's what you guys are using every day in your phone or in your laptop. So I dig a little bit more for certain application. So I'm personally using iPhone and I'm using MacBook. So I searched a little bit for the Apple Silicon. So probably you've heard that Apple is making their own processors. So there are M2 series and M3 series. Again, this is coming from the Wikipedia. And in case of the M2, depending on the application or the chip performance, it could be either 20 billions or 40 billions. And in case of M2 Ultra, it will be 134 billions. That's a lot of transistors, right? And in case of M3, it's even more advanced technology node. So the previous one was using N5, meaning the 5 nanometer technology. And then this is 3 nanometer technology from TSMC. And here it could be up to 84 billion transistors. And they didn't reveal the die size for those, but there were die size information for the M2 and M2 Pro. So you can see that here, die means the small piece of wafer. So you would see the like circular wafer from the news or something, and then it will be cut into multiple chips, multiple pieces, and that's eventually sitting inside of your like black package. So that's what we call die, a small piece of wafer. And you can see that it's only 155 square millimeter, meaning that it's like 12 millimeter by 12 millimeter. And the M2 Pro is like 17 millimeter by 17 millimeter. So it's literally the size of your thumbnail. It's like that small. And within that size, we have like 40 billion transistors in it. So it's amazing, right? How people made this. So this many transistors are sitting inside, and then they are not just packed together, right? It's not just molecules, right? They are small logic units, so they need to be connected each other to perform certain functions. So thinking about that way, it's pretty amazing, even though probably I'm just watching shorts or YouTube all the time with this advanced technology, but still the supporting the background of this, human lifestyle, we are supported by this amazing technology. And you can see that the core speed is around 3.5 gigahertz or 4 gigahertz, meaning that within 1 second, there will be 4 times 10 to the 9, power of 9 pulses, right? This pulse, within 1 second, there will be that many pulses. So that's the chips that we are using every day. That's pretty amazing. And so I will talk about the electronics design automation now. So maybe you got a feeling how complex that is, right? But before going into the detail of this step, maybe still in this page. So let's say you are the engineer to think about how to connect those 40 billion transistors together, right? Then you can imagine that this is not a very trivial problem to solve, right? And not just the connecting, but we also need to consider the communication weight. So I will bring some analogy for that. So let's say there's a person A, and he or she has a friend named person B, student B. Student A and student B, they are talking a lot. So they are talking maybe 10 times a day. And there's a student C. C is talking to A maybe 5 times a day. And there's a person A's mom, right? Student A only talks to his or her mom once a week, right? So depending on the frequency, how you frequently communicate, there should be some different weight. So you can imagine that there will be, even though this is a transistor, there will be a small logic unit. We call that gate, like an AND gate, NOR gate. Probably you've learned some of those. So some smallest unit to do some logic function. So typically a few transistor will make one gate. So let's say each of you are one gate, and then you are connected to each other. Person A needs to be connected to person B, and also person C, and also the A's mom. So they need to be connected each other to have the communication. And let's assume that you need to actually physically go there, person B's house, to talk to each other, right? And under the situation that A and B are talking maybe 10 times a day, it is better to put the A's house and the B's house close together because they are talking a lot. It's better to travel. It's better to be close together so that they can travel easily, right? And maybe it's okay a little bit far away for C's house because they only talk maybe 5 times a day. Maybe mom's house can be a little bit farther away because you talk maybe once a week or so, right? So you can represent each of the gate as a node of the graph. And then the communication path can be an edge of the graph. And depending on how you frequently communicate, there will be a different weight of this graph. Now the problem becomes like a graph optimization, and the scale is large, so it's a large graph with billions of nodes and edges. But now we will need to think about what will be the optimal way to make this whole communication efficient, right? How we can support the A and B's frequent communication, and while still supporting A and A's mom's communication. And you can think about the connection between billions of components, how to place them and how to make them routed. That will be a big issue, right? So that's, roughly speaking, that's the area that I'm working on. So that's the problem that I'm solving. So moving on to the next page.
Can I have a question now on the previous slide?
Sure.
Yeah, so about the connecting so as we move up from 5 nano to 3 nano, how much can you increase the speed of the clock?
Oh, the clock speed, according to the spec, it's not that much, right? It's only like 3.5 gigahertz to 4 gigahertz. So right now, the bottleneck of increasing the clock speed, as far as I know, is because of the SI issue, the signal integrity issue. Because if the clock speed is getting higher and higher, then there will be it's more susceptible to the noise, interface, electrical noise. So even though the processor node is decreased a lot, but still the clock speed is not linearly increasing at this moment, if you are asking in that way.
Yeah, thank you.
So electronics design automation is the field or a market segment from the business point of view, consisting of software, hardware, and services in the semiconductor devices planning, design, implementation, verification, and manufacturing. So typically the modern chip design flow is starting from the system specification. We would like to have, for example, like 4 gigahertz, this chip, CPU, and then there will be architectural design. Initially, designers or engineers will write some high-level code. It could start from the C or C++, and then will be synthesized into the hardware descriptive language, and eventually to the logic design language. There are special language to describe the hardware. And then there will be logic synthesis to make this kind of a net list, basically a graph. And after that, now we need to place each of those components in the canvas and route them, and this making the connection. And this connection is 3D, by the way. It's not just like 2D, so we need to use multiple layers and going up and down. And after that, there's a physical verification and sign-off, meaning that we just confirm this design, and the design will be sent to fabrication, such as TSMC or Samsung Foundry or Global Foundries, and they will make this kind of a wafer, and each of those small piece will be a chip, and this will be packaged inside of a typically black thing, right? That's what we call package, and then that will be the chip. So if you just open your laptop today, there will be a circuit board, and then this chip package will be attached on top of it. So apparently there's no way that human can manually do this, all those stuff. So each of those steps will require very sophisticated and specialized software, and the EDA vendors or EDA companies are selling those softwares to the chip designing companies such as Apple or Samsung, LG, Hynix. All those chip manufacturing companies will have to buy one of those EDAs or many of those EDA tools to achieve their goal in each of those steps. So that's what we call electronic design automation. Now let's think about the challenges in applying ML or AI in this EDA industry. So as you can imagine, there are hundreds of billions of transistors or complex interconnects to connect in between them. So the complexity is really humongous. And then we need to consider multi-domain constraints such as timing. Timing means to meet the clock speed. And also the power, for example, that's the chip for your cell phone. There will be the power limit that we need to satisfy. And there will be the thermal, especially for this dense transistor situation. There will be even though there will be a small heat dissipated from each transistor, altogether that will be the big thermal issue. So yeah, that's the issue that we need to consider. And then also the electrical noise and manufacturability. So the core EDA problems are naturally NP hard because of the scale, and the design space is astronomically large. So typically people rely on the heuristics, and then there are many strategies for each of the sub-steps of this EDA flow. And another challenge is the data. So as you can imagine, TSMC, for example, would not want to share their recipe with other foundries for sure, right? And like some other chip designing company wouldn't want to share what they know with others, right? Because that's their own IP, that's their intellectual property. So it's rarely shared publicly. So there's not enough data in a public domain. And complex data representation, as I mentioned, the data is not just tabular data. Often that can be a complex graph structure. And on top of it, it also involves geometric data because we need to know what kind of wire rectangles are used here, and then what kind of transistors are placed here, and so on. So multiple levels of logic abstractions are needed. And another thing is, as you could see from the previous slide, so from M2 to M3, probably took maybe a couple of years to get there. So the process node itself is emerging very rapidly. So the training data that we used for the previous node may not be very useful for the new node. So that's another challenge in the EDA industry. And another thing is the cost. So unlike most of the softwares in this EDA, especially if it's already signed off and then if it's already sent to the fabrication, and after that, let's say you found some error in the chip design, then it will be a disaster. So to refabricate everything, and sometimes you may need to go back to the previous step, right? Go to the previous step and then redo all of those. That will take maybe tens of thousands of engineers' effort or thousands of engineers' effort, and it could easily take several months, or even years. So any errors in the chip design can cause the astronomical cost in manufacturing and redesigning. I think that's the reason why the chip industry or EDA is a little bit more conservative to apply the ML or AI because of the cost. And long design cycle, typically going from here to there takes couple of years, I would say. So that's a long design cycle, and we also need the domain expertise. From my personal point of view, this is a big hurdle because I want to hire a good engineer who can understand both domain, right? The chip industry, chip designing domain, and also ML. So we often hire people just for the chip design and then try to educate for ML, or vice versa, try to hire ML person and then educate for the chip industry. But both are very complex and needs several years of expertise. So it's not easy, yeah. But at the same time, we have some favorable characteristics of EDA for ML and AI. Naturally, this chip design process is based on the data, right? So unlike the biology or some natural things that is developed without data, from the beginning of the transistor, when we make certain transistor, that means there should be some record or log to make that transistor on that position, right? So because this EDA itself is based on the software. So although mostly not shareable, but the EDA process itself generates enormous volume of data. So from each of those stages, simulation, verification, those will generate a lot of logs and reports. And also another characteristic is it's very well-defined metrics. So we often talk about the PPA, that's the power performance. Performance means clock speed and the area of the chip. So that's the metric we are measuring. So when we change certain thing, if the PPA is degraded, then we don't take that whatever proposal, right? So from my daily work, let's say I'm in the routing team, and then we have this kind of routing and then the other routing algorithm. So which one to take, it's very clear. So based on the PPA, we can take the one. So it's very clear. So in that sense, it's well-suited problem for the ML or AI because it's very clear. And then another example will be the power, clock speed, die size, and then the yield, manufacturing yield will be another metric. And cost, actually, it's the same thing. It's very expensive. So all the designers or designing companies, they want to reduce the cost as much as possible. So let's say it was previously 2 years to design certain chip. With the ML and AI, if we could reduce that by half, 1 year, that will be an enormous saving for them. And also, if we can reduce the defect, for example, so that we can increase the yield, then that will be directly related to the cost. So that will be related to the huge cost saving. So that's why, even though it's a bit conservative, many chip designing companies and also the EDA industry, they want to use the ML and AI nowadays. Okay, so I will briefly go over the trend of the AI ML in EDA and chip design. Mostly it's focused on the ML because I was relying on the survey. So recently there are some products relying on the LLM, but I didn't cover in the majority of this slide. I will briefly mention that in the conclusion. So as I mentioned, those are some key components of the EDA workflow. So we have high-level synthesis. So the goal is changing the C++ or C, System C, into the hardware descriptive language. And then after that, we have logic synthesis to change the RTL, that's another hardware descriptive language, to the optimized gate-level netlist. And then physical design is something that I explained briefly with the analogy. So how we place each component and route them to achieve the best PPA. And then verification and testing. And I will go over each of those. So for the high-level synthesis, ML has been used for the faster PPA prediction or guided design space exploration for optimal directives. So at this moment, we don't know what will be the final timing. This is very early phase. So unless we go through all the stages from high-level synthesis, logic synthesis, physical design, and so on, we don't know the actual timing. But we could have some rough estimation. So far people were relying on the certain implementation, very simple implementation, and then achieve the bit stream. So as you can imagine, even though this is simple implementation, that is time consuming. So we had to simulate what will happen later in the chip design to estimate the timing or like sometimes power and so on. But with the ML predictor, now people can use faster and more efficient way of the estimation. Let's put it in that way. So there's a paper. This is a little bit older one. This is 2018, but this is one of the earliest work in this field to use the ML prediction. And right, so they collect the C2 bitstream flow and use this data and use the various clock speed and estimated the final result. Since the EDA itself is one field, right? So it's impossible to go over the detail in this short seminar, but I would like to give some flavor or some high-level outline for you in case you can have more interest in this area. So for the high-level synthesis, main task that we were interested in were result prediction or active learning and improving the existing algorithm. So people used some simple models such as random forest or decision tree. And then later they moved to ANN, and some people used graph neural network as well. That's the overview. And in case of the logic synthesis, so this is how we translate the high-level register trans-level descriptive language into the netlist. Netlist is the graph that I described earlier. So gate-level netlist. And again, this logic synthesis is done by certain software tool. So like Cadence or our competitor Synopsys, they also sell this kind of tool to automatically do that. And depending on how we partition the circuits, so you can think about we have a graph, billions of nodes in there, and probably we can cluster certain graph together, so that we can have certain partitioning for the more manageable size. And depending on how we cluster them or partition them, the performance can vary a lot. So that's involved in this logic synthesis as well. So predicting the best script and flow to do that, and what will be the quality of result at the end. And people also use RL for generating synthesis flow. And this is the work from 2019. They used the DNN to automatically decide what kind of optimizer should be used for different portions of the circuits, or how to divide, how to partition the circuits. So that's part of the logic synthesis. And physical design is where I work, right? So Cadence has the software named Innovus. That's the product that I'm working on, and it is the place and route tool. And when I was in Google, the Alpha Chip project, that was also related to this place and route. So at that time, this work is that Alpha Chip work, and the problem that we wanted to solve was how to place the macros. Here, the macro means the bigger blocks. So you can see that smaller blocks like gray things here, and then the bigger block, purple blocks. So the purple blocks are so-called macros. And depending on how we put those macro, the whole performance of the chip can be changed. So at that time, this work was using the RL and GNN to solve that issue. And the metric, the goal that we wanted to achieve was the smaller congestion and then achieve the better timing and power. So this one was one of the early work, and there were many other works related to that. So this is about the placement. And in the meantime, for the routing is like how to make a road between the component, right? And unlike the real road that we are using with the car, so in the in this electronic design world, certain path should be used for certain signal only, right? They cannot shared with different signals. Let's put it in that way. So let's say, let's go back to the analogy, and then person A wants to communicate with person C, then there should be a special route just for that purpose, right? And if person A wants to talk with person B, that should be a separate route. So each of those connects should be separated, so they cannot share together because that's a different signal. And naturally, if you route that many roads in a certain limited space, there can be some supply and demand issue, right? So let's say you have a space that can serve for 10 roads, and now you have a demand for 12 roads, then there's no way to go for those two signal path. So the goal of routing is to prevent that kind of situation. We need to allocate the resource while minimizing the communication burden, meaning that the timing should be minimized and also power should be minimized, but we also need to guarantee that there will be a route to connect to each other. So when we say the routability, that means the supply and demand are well aligned. So there's no more extra demand out of supply. So that's what we call congestion. And typically this congestion can be an area that the CNN can resolve, can help a lot. So people use CNN or CNN related models a lot. So to reduce the congestion, and by giving this feedback to the router can resolve the congestion much earlier or more easily and so on. So again, this is a little bit earlier work. It was just based on the CNN, but nowadays people are using more advanced models. That's for routing. This is for the timing estimation. So timing means, as I mentioned, there will be like 10 to the power of 9 bits within a second. So the signal electrons need to reach from certain point to the other point within that small time slot. So 1 nanosecond, actually 4 gigahertz, that means like 250 picosecond, right? So 1/4 of nanosecond, within that time frame, the electrons need to move from one point to the other point. And That's the constraint. That's the constraint that we are dealing with, and eventually from one point of the circuit to the other point of circuit, how the electrons can travel, right? So of course there are different strategy how to boost up the electrons so they can speed and to arrive earlier. But then there will be a trade-off between the power, how much power we will use to boost up the electrons, and then there will be the thermal issue and so on. So anyhow, so there is a sign of timing prediction. Again, this circuit will be represented as a graph, and then we can use customized GNN to extract information from netlist. And in this paper, they used CNN with masking techniques to extract further information from layouts, like a visual thing. So they extract more information and use that. So for the summary of this logic synthesis and PNR, so far people used like DNN, CNN, GNN, GAN in reinforcement learning and so on. Again, this survey paper is a little bit outdated. So this is 2021. So it doesn't involve the later, most recent ones using the LLM and so on. And verification and manufacturability, I will just go quickly. So for the verification and manufacturability, since we already covered in the challenges and benefits of adopting the AI and ML for EDA, so the key area is, of course, yield enhancement. So yield means, let's say you have a wafer, and that has 100 chips. You can generate 100 dies. And because of certain issues, right, certain defects and so on, let's say you can only use 70 chips out of 100, then the yield is only 70%, right? So the 30% will be just wasted. So if we can enhance the yield a little bit, that will be directly resulting the cost saving. So that's a very important area. And especially for the 3 nanometer and moving on to the 2 nanometer and so on, the transistor sizes are so small, so there are higher chances to have defect. So it's even more important than before. And key players. So probably you've heard foundry names such as TSMC, Samsung, GlobalFoundries, Intel. Intel also has their own foundry. Equipment vendors, so they supply the equipment to the foundries, like Applied Materials, Lam Research, and so on. EDA or software, so Cadence, Synopsys, Siemens, those are the 3 major EDA vendors. And hardware providers like NVIDIA, AMD, Intel, Google, Amazon, and Qualcomm. And academia, there are many other academia interested in this field. So for the verification, I will not go into the detail, but the basic goal is to generate the test set effectively to have better coverage. So it's somewhat similar to the unit test in the software development, right? So let's think about the case where we have the 100 inputs of certain block. So there are 100 inputs, and each input can have either 0 or 1, right? Then we would have 2 to the power of 100 cases to test, right? And depending on the number of inputs, that will be increasing exponentially, right? So if the certain combination of input can eventually reach to the same output, right, then we can reduce that kind of cases, right? So how to cover the vast majority of the input and output combination with the smallest set? That's the task for the testing and the verification. And then this is one of the early work, 2019, and then they used the random forest classification to predict the synthesized outcome, and then reduced it effectively. And this one is a little bit interesting. This is a manufacturability. So now we are dealing with the nanometer scale, right? So as I briefly mentioned earlier, so when you look at the inside of the chip, there will be transistors or gates, and then the interconnects in between them. And the size of those are nanometer scale. And to print that, physically print that in the wafer, so we use laser and all kinds of different techniques are used. And because of the wavelength of the light, the nature of the light, it's not printed as it is, right? So you can think about if you just cut certain paper in certain shape, and then if you put the paint, then the bottom paper will get this mask shape, right? It's similar to that. But unlike the paint situation, we are dealing with the light laser, right? So that there will be the diffusion and then the diffraction and so on. So it's not printed ideally. So even though we initially drew like blue shape, this is like this this is polygon, right? The blue shape. Eventually it will be printed something like the red one, right? It's not like very sharp edge. Yeah, that's the nature, right? That's the nature of the light. So what people are doing is they put additional shape to adjust this shape. So instead of having the blue shape, if we put this green shape, eventually the actual shape after lithography will be closer to the rectangle. And this one is another example. So that's the area we call optical proximity correction. So we correct it to make a more rectangular-like shape or polygon-like shape. So instead of having the target shape only, they put some helping structure like this, helping lines. And having this one actually helps to make this more rectangular or polygon-like shapes. So that's the optical proximity correction. And how to generate this itself is a field of study. And then for this manufacturability, some people did some GAN OPC, so the mask optimization, using the generative adversarial network. So to predict what will be the actual pattern and then give the feedback to the original design. So that's also another area of the study. Okay, so I think I already covered most of them. So we have key players such as EDA vendors. And nowadays, Cadence, Synopsys, Siemens, recently they also started to use LLM. So Synopsys AI, Cadence AI, or AI-driven tools, RL for PPA out, and also the co-pilots. As far as I know, all of those companies are working toward the co-pilot for each of those design steps. And then chip manufacturers like Google, NVIDIA, Intel, AMD. So they are also internally using AI, just like AlphaChip. So that was coming from Google, who is actually designing the chip. So they also working on that. And then GPU acceleration. NVIDIA is actively doing the research for this area.
Some noise coming.
Sorry. Okay. So nowadays, it's not just the one key player like drive the stream. It's not like that. So the partnership is getting stronger and stronger because, for example, from the EDA vendors perspective, we need the collaboration with the designer and also the foundry more and more. So even for this AI or ML projects, so we need to collaborate very closely to get the data together and to get the results together and so on. So that is already changing the landscape of this industry. Okay, so emerging frontiers and future trajectories. So LLMs are used more and more, sometimes people use the HDL code generation itself, just like a Copilot, right? For the GitHub Copilot and so on. So the hardware descriptive language or Verilog can be auto-generated by the LLMs and also copilots. We still have some hurdles like reliability and security, especially security, because those are IP for each companies and we need the domain-specific data, but it's moving toward that direction. And then GNNs to optimize the circuit itself. Yeah, it's doable, but not all the data can be represented as by graph. And again, the security is another issue here. And then all native EDA. So it will be ideal if the entire flow can be optimized or automated by the AI and ML all together. But that will be a long-term goal, I think. I think it makes more sense to have each of those steps to have very specialized ML or AI assistant to help EDA more efficient. And then we also need the open benchmark and data sets. As I mentioned, each of those data are the proprietary for each of those companies. So it's very hard to be shared, but yeah, I think the whole industry needs to work together. If, for example, for the older data, we can make it open so that the academia can use it. So I think probably we need that effort. And domain-specific applications, as I mentioned, it will be better to have certain steps to use certain ML or AI, like logic synthesis or package design. And then for each of the design-specific application, the chip will be very different, like AI chip, like TPU, NPU, or automotive chip, or nowadays quantum computing, or superconductors, and so on. So each of those will have a specific goal, and then the ML can be tuned, ML or AI can be tuned further to meet the specific target. So yeah, AI and ML already have changed EDA a lot, and driven by complexity and scaling limits. And now it's already essential for the whole design process. And the key advancement is mature prediction task or ML-based optimization or massive acceleration. And we still have lingering challenges such as data access or quality, trust issue, that's the big thing, and then scalability and skill gap, which is personally the big issue for me to hire people. So those are remained as significant hurdles. Yeah, I think that's all for today's talk. This is my work email. This is my personal email. If you have any question, like my personal career journey or today's talk, please feel free to reach out to me. Yeah, thank you.
Yeah, thank you very much for great talk. And a great kind of introduction to the AI and this design, chip design. So, any questions? Please feel free to ask.
Let me start first. I actually drove by the headquarters Cadence in the Montague Expressway, Trimble. I never know what the company is doing. Now I finally know. So I have two questions. So first one is maybe advice to our students. So for your job, did you hire software engineering and then to learn domain knowledge, or you hire the people know chip design and then learn machine learning? So which one? Because the machine learning, I think you list there, it's not that complicated. So I assume the domain knowledge is more difficult.
If I can change the question a little bit, what kind of people you pay more?
Well, salary differs based on the engineer's capability, not based on the job. So because we need both ML people and also the software engineer. Even before adopting the ML, actually EDA is somewhat in between the electrical engineering and also the software engineering. We need the both domain, right? The chip design typically the EE specific knowledge and also the software, because eventually we are making the software with C++ and so on. So even without ML, it was in a cross-functional, we need to understand both domains. So that was a challenge already, even before ML. So what we did was we tried both ways. So hiring the electrical designers and then train for software design. Of course, the person needs to have some knowledge about the software design. So the engineer needs to, I mean, they need to code. So they need to know how to write a code. That's the mandatory thing. But if someone has the knowledge in the chip design, then we will foster them to learn more for the software design. And vice versa. If I just pick up one from the pure CS graduate, right, then I need to educate that engineer for the chip design domain knowledge. So that was already a challenge. Now we're adding yet another domain, which is the ML, right? And people from ML often don't know about the chip design, of course, right? So it takes some time. So after hiring, we need to go through, maybe it will take more than a year or so to get used to all the terminologies and the flow. So if we hire a ML engineer, then we need to educate that engineer to get used to this terminology and the flow. Yes, so we do all of those. So we pick up, as long as the good engineer, someone is a good engineer, they can pick up quickly. So yeah.
Can
That's
you
the-
can you
Alright,
give
the second-
a short give it number on how much the engineers can learn from the beginning?
You mean the timeline?
No, I mean what's the salary range for the initial
Salary
what-
range.
in
Levels,
the field,
FY
not the specific your company. Yeah.
Yeah, Levels FYI has all the salary information, public salary information. So as far as I know, our Cadence doesn't have that much difference between the software engineer and the ML engineer. Yeah.
Mhm.
But you can query it from the Levels FYI, all the big companies.
Okay.
Yeah. And the second question, do you have the second question?
So the second question is, what is the business model of Cadence? Do you sell software or you take a contract and design for the
Oh,
company?
no.
Because
We sell
this
software.
is really, because a lot of specialized chips now. I don't know how
Yes.
easy. There's a GPU, previously CPU, and then gradually you have a TPU, you have this and that. They're so specialized. So
Yeah.
I don't know, is software able to cover all of that, or Cadence only covers certain type of chips?
So even though it sounds very different in an essence, like for example, for the place and route, right? How to place them based on the constraint optimally. I mean, not optimal, but better. And then how to connect them. So those kind of essence is the same. So people can use the same software for the TPU and GPU and the CPU or mobile AP. Or the memory controller, they can use the same software. So that's the difficulty that we need to serve. So the business model of Cadence is to sell the software. So actually the license of each copy is pretty expensive. That's what I heard. Because to develop that kind of software, we also need to invest a lot with thousands of engineers together. So that's the reason. Yeah.
I mean, there's so many fabless companies, around the world, so
Yeah.
they have to use these tools.
Exactly.
Ask a question?
Sure.
So
Why don't you
from the
introduce yourself?
yeah, so I'm a freshman undergrad in Seoul National University. My name is Kim Sung-won, and so a lot of the models here, like for example, random forest models are not really large models. in the sense that their parameter count isn't that large compared to the really large models we use today. But at the same time, large models don't necessarily need to be large language models. So we can actually, train large models on directly the hardware data that, the data from this whole design process. So do you see like a trend of increasing model size in this field too? And like if you can give us numbers, like in the state of the art models that you use, like what are the parameter counts for CNN, GNN, or RL?
That's a really hard to answer question because it really depends on the usage. So for example, I mentioned even in the place and route, even though I just put the place and route, but there are also optimization team as well. So doing all kinds of timing optimization. And within this route, there will be a global route and detail route, maybe some DRC cleaning up. And for the placement, there will be global placement and then like macro placement, global placement, detail placement. So depending on the usage, each team can develop their own model, right? Because they would have their own problem to solve. So it's not just a one big model can serve everything, but each engineer or each team, sub-team are developing their own usage model to integrate with ML. So, and maybe some team are just focusing on the certain problem, subset of the problem, not the entire graph, right? So it's really hard to answer. To be honest, I don't know the whole picture, right? So of course the model will be increased as time goes by, but I don't have the number because of this kind of situation. Yeah.
Any other questions? I have a question regarding the nowadays the stacking the chips is becoming more and more important than before. So what kind of changes do you see in this EDA industry? And also, for example, in Korea, we have a company called Hanmi Semiconductor that provides TC bonder for HBM3, HBM production. And it looks like and other companies are trying to follow, but they are behind. There must be. It looks like there's some gap, and I guess AI may help for these companies, these competing companies to to accelerate innovation and in this field. Do you have any idea? I mean, the two questions.
So right. So actually my PhD dissertation was somewhat related to the 3D IC as well. So there are different perspective of 3D ICs. In case of HBM, that's just for the memory, right? Usually we have the memory controller and then we have stacks of memory and they are kind of homogeneous in terms of the functions, right? They are just memory, like very regular memories. So of course, I'm not saying that's easy. It's also very difficult. That's why Hynix is doing so well. I mean, only Hynix can do it well. And the yield.
Micron is also doing.
Micron is also doing, and then hopefully Samsung can do it well as well. So as you can imagine, the yield will be an issue, right? So if we have more and more stacked via, let's say that I mentioned that like 70% of yield, right? And then if you multiply them, there will be a huge degradation of yield. So if ML AI can help on the overall yield estimation, not just the individual, of course, the individual die yield is also important, but the bonding itself can cause the defect, right? So how to simulate the holistic view of this yield and the manufacturability will be a big issue for that stacking itself. That's coming from the nature of the stacking itself. But the second part is more like a heterogeneous stacking, meaning that not just the logic stacking, I mean, not just the memory stacking, people can think about the logic stacking. For example, there's some AP, some processor here, CPU and GPU and TPU or something like
Right.
some different processors stacked together. And then in an extreme case, let's say that we are putting certain logic part to this die, this level, and then the other die, and they need to communicate vertically as well, right? So that will add another dimension of the circuit optimization, right? So when we talk about the placement, it was still in a 2D. So the canvas, and then we were putting the alpha chip was putting the 2D placement. Now we need to think about the 3-dimensional placement, right? And at the same time, it needs to have the vertical parasitics, meaning that there will be the delay, timing, physical delay, and then there will be the thermal issue. And so all those constraints will be getting more and more complex. So the graph optimization is still there, but it will be even more complex because now we need to deal with the 3-dimensional one. We are not there yet, but assuming that we are moving toward that, then that will be adding another layer of complexity, and definitely AI ML will help for that. And where to put certain module, which layer, which floor, that will be a big thing as well. And it could be a little bit related or unrelated, but in terms of the thermal, so the stacking will naturally increase the heat, right? So it will give the poor heat dissipation. And so far, people were relying on the software like FEM, like that's a physics-based like mesh structure, how to simulate the nature of the thermal dissipation or something like that. So that is also the software Cadence or Synopsys we sell. And even for that, if the 3D structure is getting more and more complex, the mesh structure, the number of mesh will be humongous, right? So how to optimize that, probably AI can help a lot for that as well. Yeah.
So would that be a good topic for new startup? Are you not interested?
Yeah, new startup. It will be
Well,
worth
it's going to be good, good, great challenge, and people are raising billions now. New startups are raising billions at the moment.
Yeah, it will be a one great area, even though it will be not very easy, but the application is already there, right? So yeah, especially to reduce the simulation time for the thermal yield issues, those will be needed immediately from the industry.
Yeah, if we can bring these manufacturers, I mean, the equipment manufacturers in the
Right.
game, there will be one direction that for
Yes,
startups
yes.
can pursue. Yeah.
And especially since the HBM, Korea is leading the market, so it could be, it makes sense to have some collaboration with the industry, I think. Yeah.
Okay, thank you. Professor Yu?
Yes, thank you for your interesting and wonderful talk. I'm not an expert in this area. I'm majoring in economics. So let me ask a question for our students in economics department. If someone is an undergraduate econ major who would like to grow as an industry expert like you, what kind of advice would you like to give to such a student majoring in economics or social science or more broadly humanities?
Wow, that's a tough question. That depends on the one person's goal, like a life vision, right? So if I'm an engineer, so I cannot think of other jobs other than the engineer. But I can actually, yeah, there are multiple ways to explain.
The goal, I suppose, is to grow as an industry expert like you.
Industry expert. Yeah, since this is the we are talking about the AI and ML, if assuming that person is interested in learning the AI, right, and ML, and having the expertise, combining those cross-domain knowledge together, right? That's one way to develop one's career, because there are so many demands, right? If we use the ML or AI, there are so many demands, even for the economics and the social studies, there are more opportunities. So that's one of the way. But on the other hand, I think humanity itself has its own value, right? So even though I'm an engineer and I work based on the metrics and numbers, and nowadays more and more jobs can be replaced by AI and so on, but actually, ironically, that makes humanity study to have more value than before. So like, for example, what makes human as human, right? And how we can differentiate ourselves from a machine or AI, that will be, or the AI ethics, how to make the AI supporting human, not the other way, right? So those kind of very critical questions can be studied and answered by the humanities studies, I think, and also the social studies. And that's the crucial study probably that people need to think about. But engineers are too busy, and then they are just focusing on a small achievable goal. Okay, if we improve this one, that will be better, that will be better. But at the end, maybe we are heading to the wrong direction. Who knows, right? So in a bigger picture of the humanity, right, what will be the right direction that the entire human being needs to pursue? That will be probably the question that either social study or the humanity need to answer. And I don't know much about the economy. Maybe there can be some other area that, especially in this emerging situation, AI emerging situation, there would be some area that we haven't thought about before. So even though it seems like there's not much demand, eventually, if we are thinking about the some area that could be newer than before, then there will be some demand to grow as a professional, I think, like ethics or some social policies related to the AI, or more fundamental philosophical question. Yeah,
Thank
I
you
don't know
for your
whether I
view.
answered it.
Let me ask us a different type of question. If you
Sure.
can return to your past, say 20 years ago, are you willing to, or if so, how would you like to redesign your career?
It's a tough question.
Yeah, that's a tough question. I would do the same.
That's great.
Yeah, I would do the same thing. Honestly, do we have many undergraduate here in this seminar?
Someone is the freshman, unusual
okay. Okay.
student.
So when I was in